This is the GR3D physics archive for physics 110. This video is going to cover workout 2, hopefully the whole thing, but if not, at least parts A, B, and C. So in this problem, we have a motor that's connected to a hollow cylinder of mass m and radius r. The motor applies a constant torque in the counterclockwise direction. A massless rope is attached to the hollow cylinder, so the rope will wind onto the hollow cylinder as it turns. Mass m is tied to the other end of the rope and is initially at rest. The mass m is lifted up with an acceleration a. Physical data are given in the table below. So, good thing to start with in this one is looking at the picture and putting the words to the picture so you understand what's going on. So, this hollow cylinder is talking about is this circle, this black circle, and it has a mass m and radius r. That's important for when we calculate I, because the hollow cylinder itself will have its own mass and radius separate from the hanging mass. This motor is applying a constant torque, so we know this motor is turning something and it's telling us the direction of rotation counterclockwise. And then we also know the massless rope is attached that holds mass m down here at the end of this rope, and it's initially at rest. That's also going to be important later. It's lifted up with an acceleration a, so it's lifted up with some acceleration a. So, first parts A and B are just free body diagrams, understanding the picture, and being able to draw whatever forces are on the objects. So, it first just wants the free body diagram for a hanging mass. And so, this should just be a review from block 1 when you did free body diagrams. It's no different than a string hanging over a pulley, except this time the pulley can rotate. So, the hanging mass, we want to start off with our mass, our block of mass m, and so in this case we have a string connected to it, so there's going to be some force coming up out of it. We're going to call that the tension from the string, and then there's also the force down from gravity. And make sure when you do free body diagrams that you put your axes in there. Luckily this question reminded you to do that. Oh, I'm going to draw it a different way actually. I'm going to go this way because we know it's going to rotate left. I'm just going to make this my positive y and my positive x. Oh, sorry, wait. I'm going to call that positive x and positive y instead. And then when I first did this GR, I put an up arrow saying that acceleration was moving upwards, just as a sanity check for myself. So that one was pretty simple. That's block 1 material. Part B is where we bring in block 3 material. So we now need the free body diagram for the actual hollow cylinder. So you want to draw your circle as your cylinder. And in this case, we have two forces acting on it. We have the motor. Whoopsies, what happened? We have the motor that is rotating this thing, let's see, counterclockwise. So we have to apply a force, and in this case, it's not just a force, it's the torque applied by the motor. Because the motor isn't giving a linear force to this hollow cylinder, it's rotating the cylinder, and so if anything's rotating, we're going to be using torques instead of linear forces. So the torque of the motor is going counterclockwise, and then we also have the other force coming off of the cylinder from that string. And that's perpendicular, or I guess tangent to the circle. Like if this is our center, this distance here would be a 90-degree angle. So this force going here is also our tension. Labeling things in terms of axes. Again, I called this my positive x and my positive y just because I liked to deal in terms of x. And then, again, I drew an arrow up for positive a, just to remind myself that positive acceleration is when it's moving upwards, not downwards. Or else I would have been dealing with a lot of negative numbers. Another thing you can draw is, I don't think you need this on yours, but if you want to remind yourself that not only is A going upwards, but also angular acceleration alpha is going counterclockwise in the positive direction. That's another thing you could add there, but I don't believe you would receive or lose points based off of that. Okay, for part C, find the magnitude of the tension in the rope used to lift the mass M. So, whenever we were trying to find tension back in block 1, the equation they always sent us to was sum of forces equals mass times acceleration. And so there's no difference in this question because when we're just finding tension, we're not having to deal with anything in terms of rotational things because we can just deal with our block that's hanging from the string to figure out that tension. I'll write it down and that'll make more sense when I write it down. But if we start out with sum of forces equals mass times acceleration, I'm only looking at the block right now. And so I need the sum of forces for the block, and that's going to equal the mass of the block times the acceleration of the block. Again, I'm not looking at the hollow cylinder because we don't need it to find tension in this case. So the force is acting on the block. We can go back to our free body diagram. I have a force down from gravity and a force up from tension. Since I established the up direction is positive, I'm going to say that gravity is negative. So a minus mg plus my tension equals ma. And remember, all of these masses are the mass of the block, not the mass of the hollow cylinder. Just a reminder. So I need to find tension. So I'm going to get tension by itself. So I'm going to do ma plus mg. Okay? And the good thing here is we can plug in all of our numbers because it gives us the mass of the block, it gives us the acceleration of the block, and we know what gravity is. So we can say tension equals mass. What's the mass? 65 kilograms. Times acceleration, it gives it to us as 0.3. Here, I'll go back up to where it shows that. In the table, we have mass is 65, acceleration is 0.3. And then mg, we have 65 kilograms, and then gravity is 9.8. Plug it into your calculator, and we get T equals 656.5 newtons. So in case you were worried that you had to incorporate the cylinder into this question, you probably would have gotten to the point where you didn't have enough information, or you would have gotten to a point where you couldn't solve for T easily. And so it's good to start with the block, and then if you got to a point where, oh, there's one more unknown, I need to calculate that, then you can incorporate the hollow cylinder. But I would recommend, if you're trying to find tension, start with as few things as possible. And in this case, we were just looking at the block, and it made it a lot easier. And this is directly from block 1 material. So hopefully you could get these 7 gimme points on this one. Looking at part D, we'll go ahead and do D and E. I think we have time for that. Find the magnitude of the torque provided by the motor. Okay, so if we look back at the torque provided by the motor, if we look at our free body diagram here, we don't know what that torque is, but we can do a sum of forces equation to figure out, because we just found that tension. Now we know what that tension is, which is the only other force acting on that cylinder, and we can figure out the T motor from there. So in other words, we can do pretty much the exact same thing. It's just a little change in notation. In this case, since we're dealing with angular things since we're dealing with torques rather than forces, we're going to use sum of torques instead of sum of forces. And we're going to say that the sum of torques equals I alpha. That should be on your equation sheet. It's the same logic as sum of forces equals mass times acceleration. It's just in terms of torque and angular things. So if we start plugging into this, the forces acting on our hollow cylinder is the torque from the motor, and then the tension from the string. So since I made the counterclockwise direction positive, I'm going to say that the torque of the motor is positive, and I'm going to say that the force of the tension in the string is negative because that's going in the opposite direction. That's pulling in the clockwise direction. The only thing to be careful of here is tension is a linear force right now, and we need to be dealing in terms of torques. And so, if you saw back in our multiple choice questions, let's see if I can find it. Question 7, it's almost this exact same thing. We have a force applied on the outer edge of our circle, And then our radius is the perpendicular distance between the two. And so in order to turn this force of tension into a torque, we just have to multiply it by the radius. That also comes from the equation that torque equals RF sine theta, but again, sine of 90 is 1 in this case, so it's just torque equals RF. So it's going to be tension times the radius. So these are our only two forces acting on that hollow cylinder, and that's going to equal I alpha. So I, in this case, it's a hollow cylinder. So let's see, our equation, I believe our equation for a hollow cylinder is just mr squared. Let me check that. Yep, hollow cylinder is just I equals mr squared. So this is going to be mass of the motor, or sorry, mass of the hollow cylinder times the radius of the hollow cylinder squared times angular acceleration. Let's see, what does it tell us? So we're given acceleration of mass A, but the only thing is we need to be dealing in terms of angular acceleration. So we just need to know that angular acceleration is A over R. Wait, no, that's wrong. A times R, I believe. Wait, let me check the formula sheet. Yes. That is... Wait, I had it right the first time. A over R. Okay. So, if we know what our acceleration is, we can just plug acceleration over R in for our angular acceleration. Okay, so now let's plug in some numbers. We need to figure out the torque of the motor, so that's going to stay torque motor. Tension, we just calculated that, is 656.5 times the radius of our cylinder, which is 0.75, equals mr squared. So mass of the cylinder is 120 times the radius is 0.75 squared times the acceleration was 0.3 over our R of 0.75. Okay, so plug and chug. Let's see, I didn't calculate this one beforehand, so let me calculate that real quick. So I do 120 times 0.75 squared times 0.3 divided by 0.75, and I add 656.5 times 0.75. And I end up with a torque of 519.375. And that should be Newton meters. Okay. Okay, moving on. Last one. How many revolutions will the cylinder make in the first 6 seconds after the motor starts applying torque if the system starts from rest? So, again, we're given a lot of information here, and it's all about knowing what you're given and determining what equation to use from there. So if we're starting, it's asking for revolutions. It's giving us a time of 6 seconds, so I'm going to write that down. After the motor starts applying torque, if the system starts from rest. So my omega initial is 0. So, let's see what we can do here. So if we're looking at a lot of these problems when it introduces time into the equation, what we have to look at is kinematics, because none of our other equations deal with time except kinematics. So if I need to figure out, I need to figure out revolutions. Another way of saying revolutions is radians, because revolutions is just however many radians you're going. It's a simpler way of saying it. And so that's a theta. That's the distance we're going around the cylinder. And so we're going to need something that incorporates a theta, because that's what we need to figure out. We're given an initial omega. And remember from previous problems, we already know what alpha is, because we know alpha is just A over R, which is 0.3 over 0.75, which is 0.4 radians per second squared. So we have an alpha, an omega initial, a t, and we need to find a theta. If you're looking at your equation sheet, the one that should stick out to you is I think they called it the Big Mama equation back in my day. But it's theta equals omega initial t plus 1/2 alpha t squared. Okay? So now we can plug in all these numbers because we have a t, we have an omega initial, we have an alpha, and we need to find our theta. So our theta is, well, since omega initial is 0, this term goes away. And we're left with 1/2 times alpha, which we figured was 0.4, times 6 squared. So we get a theta of 7.2 radians. The thing is, we can't leave it like that because it wants revolutions, not radians. So we just have to do a little conversion here and say, if we want to get rid of radians and radians is in the numerator, we want to put radians in the denominator. And we need to get to revolutions. So for every 1 revolution, if you go 1 time around a circle, that's 2 pi radians. So if we do that, I am left with 1.15 revolutions. Sorry for the long video, but knocked all of workout 2 out in one video.